Hello, math fans. Starting a new playlist. I have many questions or comments or ideas about interesting numbers that I've encountered. And I thought before I started making those videos, I would start it with this, a proof that all numbers are interesting. And this is more of a joke is the wrong word. I don't know that it's such a thing, but more of just something to know. It's an example of a certain type of proof technique. Now, this itself is kind of a paradox, which I'll pull up at the Wikipedia article about it in a second. But I'm using this as an intro to interesting numbers. So if you've never seen the proof that all numbers are interesting, stay tuned. I'll do that in just a second. But I would ask, usually if I was going to present this to someone, I would say, can you give me some interesting numbers? For me, 1 is pretty interesting. 1 times anything is itself. 2 is pretty interesting. We could argue about 3, 4, 5, but I would have you give me a list of a few numbers you really like or find interesting, or your age or something. Maybe it jumps a little bit, 52, because that's how many cards are in a deck. I don't know. But you'd make this list. And this would be your list of interesting numbers. Now, part of the paradox is that the word interesting is ambiguous. But just go with me. This is something you can talk to your friends about. This is more of a discussion point, but it does highlight some things. So let's pretend there's a list of interesting numbers. Then I'll come back and prove to you that all whole numbers, and this proof is actually for whole numbers, are interesting. So before I do that, I thought I would mention a few things when it comes to working with whole numbers. Positive whole numbers, what I'm talking about now. If you ever go on and do a course in proofs, and this is just a little bit mathematical for a moment, and I grabbed these definitions from Wikipedia because I was being lazy. There's this thing called the well-ordering principle. And these little, as I say a lot, these little ideas can sometimes have major consequences. So if you go on in math, you'll eventually study this concept of proof by induction. Mathematical induction is a very formal process that's good for proving things about whole numbers, patterns, sums. It's a very valuable technique. It really stems from this thing called the well-ordering principle, which says if you give me a list of numbers, there must be a smallest one, a list of whole numbers. And it doesn't matter, the multiples of 7, 14, 21, 28. And it's so kind of simply stated, it seems like that shouldn't be valuable. But the well-ordering principle says there must be a smallest element if you have some set of positive whole numbers. And that's an important idea that we use to prove various things. Induction proofs are somewhat more bland. If you go back and look at my previous video about hippos go berserk, we proved that if you add up the numbers from 1 to 9, you get 9 times 10 over 2, which is 45. So watch that video. And then we talked about the general pattern, which is n times n plus 1 over 2. So the induction proof for this would have something called a base case, someplace you would start, and you're always hoping it's 1. And that formula does work for 1, because if you plug in a 1 on the left, you just get 1. And if you plug in a 1 on the right, you get 1 times 1 plus 1 over 2, which is also 1. And so we call that the base case. And then you prove, assume it's true for a given number, 2 plus, and this is the step students have trouble with, but assume you know it's true at a given step. Prove it's true for the next one. So if it's true for 1, then it's true for the next one. And the big part of the proof is this connection between, well, if it's true for a certain number, it's true for the next one, and that must mean it's true for all of them. That's the proof by induction. And it often involves very symbolic, this is why it works well for a proof technique, but then you say, well, what if we add one more? And then you try to manipulate using what you know to eventually end up with the same formula, but with a k plus 1 in it. And that's where we often lose students when you're proving that. You know, at UW, this would be something you would cover in a course called Math 300. But the goal would be to get it down to k plus 1, and then k plus 1 plus 1, so k plus 2 over 2. And that would essentially end your induction proof, because you would prove that if it works for k, then it works for the next one. And that involves basically saying, well, if it works for the previous one, then I can say something about all of this. I can say that is equal to that. And it basically turns it into a kind of an algebra question. If I take the pattern I already know works and then add k plus 1, can I rearrange it and show that it is the next pattern? Which you can. Multiply top and bottom by 2. And I hadn't planned this out. It's a fairly direct proof. Combine and you get k plus 1. Yeah, I don't know if you can see this, but all over 2. And then you can factor out the k plus 1. It's going to be k plus 2. Done. So the proof basically goes like that and says, well, if it works for 1. And because it works for 1, it works for 2 because of this inductive step. And because it works for 2, it works for 3. And because it works for 3, it works for 4. And that's an inductive proof of this formula by Gauss, or by Hippos Go Berserk, if you watch that video. There's another version, and it's basically based off of this same thing. It all stems from this well-ordering principle that we have the smallest one that works, and then we're using this step. There's this other way that sometimes this is used called infinite descent. It's kind of a variation on this same theme. And I'm going to have a different video about this, but if you're trying to prove that the square root of 2 can't be written as a fraction where those two are whole numbers, one way to prove it is to rearrange it. So say you have this fraction and square both sides. This is not the way I was first shown this proof, but then you get 2b squared equals a squared. And what you're trying to prove is this is impossible. It's impossible to have two whole numbers here that make this a fraction. Again, that's for another video. This is just for someone that's interested in how this is even possible. So the proof basically goes like this. If there's a 2 on this side, that forces this side to be even, which forces a to be even, which means a is 2 times some number. I'm running out of letters. Let's call it, well, it's 2 times w. That's a terrible choice. Why didn't I use c? I don't know. And so it's 2 times c. And then I'll get back to the actual thing in a second. Then when you plug that in, you get 2 squared plus c squared, so you get 4c squared. And then you can factor out a 2 from both sides, and that proves that b is even. And so then you can write b is 2 times d, and then you have 4d squared equals 2c squared. But then you can factor out a 2, and then you can say, but that means c is even. And the point of this proof is if these are whole numbers, positive whole numbers, then c has to be smaller than a. And d has to be smaller than b. Okay, so if you look at that denominator, you can say, okay, b has to be bigger than d. And then if we keep doing this process, that's going to be bigger than the next denominator we get, and bigger and bigger and bigger and bigger and bigger. So, sorry, smaller. And this denominator will keep getting smaller and smaller as we factor out all these 2's. And since we're talking about whole numbers, you eventually get to a contradiction, because you can't, and I'll talk about a contradiction proof when I talk about the square root of 2, but that's this idea of descent. You can't go down forever with positive whole numbers, so this is not possible, which means this is not possible. And that's just a different approach, this infinite descent approach, which is still the well-ordering principle in disguise, which is that you can't go on forever because there has to be a least element when you're talking about positive integers. Okay, so I hope that's sort of interesting and important mathematical proof when you're talking about whole numbers. This whole idea of induction is just a very useful proof, not just for whole numbers, but anytime you realize you have a pattern and you want to prove it for the next one, and you can find that key connection. Okay, so back to the well-ordering principle and back to our question, why is every number interesting? So So the argument goes like this. If you have this collection of interesting numbers, and then you have another list, this is list 1, and this is list 2. And you also could do like an induction proof, and you could say, well, I think 1 is interesting, and if a number is interesting, I think the next number is interesting, and there's an induction proof that every whole number is interesting. But the proof I was presented with the first time I ever heard this was, well, let's assume that this list has the not interesting numbers. Okay, so the proof goes like this. Assume there are not interesting or uninteresting positive whole numbers. I don't know how many there are, but some are uninteresting. Like I'm 44, that's uninteresting because I'm uninteresting at this age. So you have this collection. The notation for sets is this. Don't let that bug you. But we have this collection of numbers, 44, 71, whatever we think are uninteresting numbers. And the proof goes like this. But since this is a set of positive whole numbers, there, by the well-ordering principle, there must be a least number. It's not necessarily 44. Maybe it's bad I put a number in there. But there must be a smallest one. And this would be the smallest uninteresting number. And the proof goes like this. Well, if this is the world's smallest uninteresting positive number, I think that would make it extremely interesting. Because you could say, well, here's this number. It's the smallest uninteresting positive number. And we say we've reached a contradiction. Sometimes we write that. Sometimes, but we've reached an absurdity. And where did we go wrong? Where we went wrong is we assumed that there are uninteresting numbers. That was the assumption we made. So if that assumption leads to an absurdity, we say, this is a proof by contradiction, then our assumption must be wrong. So because of that, there can't be any uninteresting numbers, because if there were uninteresting positive whole numbers, there would be at least one. And because of that, they're all interesting. So you can think about that if you want. Again, that's not formal because the word interesting I did not define. So, but it's a good introduction to this idea of well-ordering principle and induction. Before I leave this, I just pulled up, this is called the interesting number paradox. And they mention here that entering this is not a formal concept. They give some famous examples. This Ramanujan, maybe that'll come up in a later discussion. Supposedly this Hardy who had befriended him, this English mathematician and this kind of, this self-taught Indian mathematician, they connected, and when he was sick in the hospital, this guy said, I was in the taxi cab that had the number 1729 on it, and he thought that was a dull number. And then Ramanujan immediately said, it's the smallest number that's the sum of two cubes in two different ways. So that's the lore of how well this person knew numbers. But it talks a little bit about the story. And then it goes on to try to find uninteresting numbers, which I thought was kind of interesting. The smallest number that didn't appear in the online encyclopedia of integer sequences for any example was 12,407. So for a while 11,630 was the smallest uninteresting number by that definition, and then it was 12,407, and then it was 13,794. But in general, whatever that number is would be interesting. And I'm just defining that in the sense that it's not in any online encyclopedia integer sequence, which is massive. So it's hard for a number to miss out. So anyways, it talks about some origins of this so-called proof. But I thought that was a fitting starting place because I have several things I would like to say about numbers I might talk about irrational numbers a little bit. I might just talk about divisibility. And I'm going to put this all in this playlist. So if you don't know how to check if something's divisible by 3 or 9 or 11 or 4 or 5 or 101, I'll talk about that a little bit. I might talk about how to cast out the 9s to check if your arithmetic is right. I might talk about hand tricks you can use to multiply by 9s. I might talk about ways you can compute percentages in your head. Lots of little, not huge things, but little things I've encountered in my life that'll be in this Interesting Numbers and Computation playlist. All right, so stay tuned for that. You might wonder, is he just going to keep making more playlists and never add to them? I'm setting the stage. I think I will add more to each one. So thanks for listening.